All right, everybody, why don't we go ahead and get started? So today we're going to begin working on basically what is the end of semester project that's going to combine all of the elements that we have worked on previously. So there's actually two activities here. The sensors and signal conditioning is basically how to build the circuits that we're going to be using. And then the second activity here is the actual guidelines for the report that you should be writing once you've completed everything. So our end goal here is to basically have two different sensors, a pressure and temperature sensor built that we will then calibrate. We will read those values out with the Arduino, so we'll use the ADC values. We'll write the calibrated values to the SD card, and we're going to add in timestamps and GPS information. So this should combine all of the different pieces of all the different skills that you've hopefully learned over the course of this semester. So just to briefly go over the report so you have a good idea of what sort of stuff you need to be recording and what the end goals here. So there's, the usual, you'll have a cover page. You'll talk about the principles of operation. How do the circuits work, which is going to be somewhat covered in the other activity. Then you want to actually, have your specific circuit drawings and stuff like that, and for the amplifiers. Then you're going to go over your software. So important things in here, you want to basically show what your data records are on your SD card. So you're going to want to use a CSV type format. You want to discuss how your software works, including a flow chart of, hey, it goes into this function does this, it loops or branches. And then how did you actually read and analyze the data? And in this case, this is somewhat simpler because if you properly format your data, reading it out will simply be putting the SD card into your computer. And finally, you'll need to calibrate your two sensors. And for this case, what we mean is you want to go from the ADC value that the Arduino will be reading out and have the actual software convert that into a pressure and temperature. So now if we go to our actual activity for building the circuits. So we're going to need our breadboards. We're going to need 4 integrated circuits called op-amps. We're going to need some potentiometers and various capacitors and resistors. Obviously, at some point, we're going to need the mega and the shield, and a power supply. So the first thing that we want to cover, actually let me shift over and show you the sensors that we're going to be using. What we're going to be using for our sensors is everyone should have gotten when their Megasat kits were shipped to the instructors. One of these pressure sensors right here. This is the ICS 1210 or 1230. There's a copy of the data sheet on the course website. For the actual temperature sensor, we're just going to be using a simple silicon diode like this, or maybe a larger one like this. And then you can see here, these are the op amps right here. It's a simple 8-pin package, but we're going to need 4 of them. potentially you could have a dual op amp that has two of them built into the same package, in which case you'll only need two of those chips. But in this case, I have 4 single op amps. So, and just to show you the resources, here is our data sheet for our pressure sensor and our op amp. There is not a specific data sheet for the diode. Mainly, one thing to note is there's not really going to be information about the temperature sensor on there. But those are the 2 things that we want to use. So you can see here is the diode data sheet, which will have our pinout, which will be important. And if we go to our pressure sensor data sheet, again, we have a pinout, and most importantly, it shows you how we're going to want to be hooking this up. So, returning to our actual activity, the first part of this circuit is we need to build an amplifying circuit, which is going to take the voltage from our 2 sensors and modify it so that we can use the full 0 to 5 volt range of our analog to digital converter. So there are a few specific examples in here and a few terms that we want to introduce. So the span of the measurement is the size of the measurement. It's the maximum minus the minimum measurement. So for our ADC, the span is 5 volts. And for our sensors, it's going to be something different. The other case is the base of our signal. So that's the lowest possible value. So ideally, we want that to be 0, but that may not be the case. So the simplest case would be, obviously, if the sensors generated a 0 to 5 volt signal, in which case we could just feed it directly into the analog to digital converter, and we wouldn't need any sort of amplifier. But that is unlikely to be the case. So the first sort of thing would be, okay, what if it just goes from 0 to 600 millivolts is the example discussed here. In that case, all that we would need to do is basically do a scaling up of the voltage. So, and we want to do that because otherwise we're going to be losing precision. We're not going to be able to use the full range of the ADC, especially when the value is small. So for that sort of situation, you use a circuit like this, which is called a non-inverting amplifier. It's non-inverting because if you have a positive signal in, you will have a positive signal out. So you'll see that there's just unlabeled resistance values here. And why that's important is if you look at the equations here, you'll see our input voltage and our output voltage are related by a specific equation that depends on how we set up this circuit. In this case, when you have no offset, like here, the output voltage is given by 1 plus R3 over R2, so R3 and R2 right here, times the input voltage. So what we call this term in the parentheses here, you'll either call it a gain or an amplification factor, because it's how much you're increasing the value of the output voltage by, or decreasing, because you could easily see that maybe I have a 0 to 12 volt signal on my input. Well, then I and I have a 0 to 5 volt ADC, now I need to have a less of a gain that is smaller than 1. But the way that this particular circuit is set up, the smallest possible value is 1, so we would need to slightly modify this. But in this case, if in our example we have a 600 millivolt signal that we're trying to get up to 5 volts, well, we know what this number needs to be, and then we have some freedom of selection on these two resistors. So obviously you don't have resistors that are in every possible value. So you want to try and pick one of them to be, you know, a standard value like 10K. And in that case, we could do the calculation for what we needed, and we would come out with needing a 75K ohm for a resistor. Another thing to note is you have this other resistor here, R1, and that does not affect the circuit gain. So generally we just want something that's similar to the value of the parallel combination here, but the actual specific number is not too important. So you would see, you know, we could pick something like 8, 9, 10K for this value, but it shouldn't overall affect our the performance of our circuit. Also, you'll note we have these capacitor, one on the input line, and then on the voltage supply line, and one on the input. So these are, in this case, just meant to clean up the signal or the power supply. So these will remove any fast changing sort of noise that we would have on either one of these lines. But all that they're doing is keeping whatever the steady value at V input is, or at the voltage supply is, at their steady value. So we don't get any sort of small rippling changes on the output. But a more realistic example, and specifically the way that what we expect to see from our diode temperature sensor, is something that goes from some positive voltage to a higher positive voltage. So not 0 to 600. In this case, for a silicon PN junction diode, which is what you should be using for your temperature sensor, we expect a 450 to 800 millivolt signal. So this is the voltage drop across the diode. So we have, so we want 450 and 800 to go to 0 to 5. Well, that's pretty simple. That's just the equation for a line. And in fact, we can plot it out. Really, we only need the endpoints here, and in which case we can get the equation for a line. So now, by doing the fit for the line, we get this equation right here. So we need a slope of about 14 and a y-intercept of negative 6.4. So we need to then put that in terms of our circuit parameters. And in this case, if we draw the circuit like this, we set it up like this, this is what that equation turns out to be. So we're inputting a reference voltage, which is we're basically setting our 0 to a higher value. And then we have a more complicated expression for the gain. As to how to derive this equation, that's a little bit beyond the scope of what we're going to cover here. But it's called, you do something called circuit analysis. It's part of electrical engineering. But you can figure out what these equations would be. So basically, we need to choose what this reference voltage is and all of our resistors in such a way that we get the desired constants. And since we only have basically two equations, we need this term in the brackets to be equal to about 14, and this Vref times R3 over R2 to be equal to about 6.4, negative 6.4. We have a number of free parameters, so we can make some picks first to just, narrow it down. So, for example, one thing we could easily use for Vref is 3 volts, or in our case, probably it's even easier to use 3.3 volts because we have a 3.3 volt supply on the Arduino. Then, for R4, we're just going to pick a round, easy value of 10K. And once we've selected those, we can calculate what the rest of these values should be by solving those equations. And if you do those calculations, you'll get these two values for R2 and R3. So those are very weird specific values that you're not likely to find a off-the-shelf single resistor that's 111 k ohms, right? But we can combine a potentiometer with a regular fixed resistor, and if we short the middle leg of the potentiometer to one of the other lines, that basically makes this whole potentiometer an adjustable resistance that will go from, in this case, 0 to 10,000 ohms or 0 to 20,000 ohms. So if we do that, we can then set the circuit up such that we can adjust these two values and get our desired 11K and 111K and 51.9 k ohms. So once that we've got these values set up, we then want to go ahead and breadboard this circuit. On this breadboard here is where I have set up that circuit we were just talking about. So you can see here's my op amp right here. I've got my connections for power and ground. I have not put the capacitors on here just to make it easier to see what's going on. And like I said, they're just for sort of cleaning up your signal. They don't affect the actual output. They just make it less noisy. And then here's one of my potentiometers, and there's my other potentiometer. And you can see I've made a little jumper that goes from the middle to one of the legs on each one of them. So this potentiometer combined with this resistor right there, that is what forms our R2. And this potentiometer right here, along with this resistor right here, that combined is what forms our R3. So you can also see that I have a number of outside connections. So I have my my 12 volt supply coming in here on the positive on the top and the negative on the bottom. I have another ground coming over here that will connect to the ground of my Arduinos, because if we're going to be reading the values off of this and using the 3.3 volt supply, we need to have a common ground, a common 0 point between the two of them. You can see right here from the 3.3 volt supply, I have that coming into my R2 right here. So that's going to come in through the resistor to pin 2 right here. And then the output is pin 6 right here. So I have a jumper coming over here. And then, so this line right here is my output voltage right here. So an additional thing that I have added over here is this is basically a simulator that will allow me to apply a input voltage that I can manually adjust. So obviously there's probably going to need to be some troubleshooting that goes on as you build this circuit. And it's going to be difficult to get the full range of your temperature sensor unless I have like a boiling container of water and or ice water handy. And that is likely to make me to have a mistake of something. I might spill it on the circuit. So I've just set up a simple potentiometer with a resistor in line that's going to give me the dummy input signal that I can manually adjust. And then when I want to use this in the real capacity, I just remove this potentiometer and install my diode right there. So if I power up this circuit, I have 2 multimeters standing by here. So I'm going to clip one. So this line right here is where my input voltage is, which is connected to this side of the resistor here. So I'm just going to hook onto that. And so that's my input signal. And I'm going to connect my other multimeter to my output signal right here. So this is what is eventually going to be hooked up to one of my Arduino analog pins. And just to switch back to the circuit, so everyone can get a reminder of what we're actually looking at. So I have one of my multimeters set up here at V input, and the other one set up here at V output. So if I switch to my other camera, so you can see on these 2 multimeters, the one on the right is the voltage of my input, and the one on the left here is my output voltage. So remember, the goal was to have it go from 350 to 800 millivolts and 0 to 5 volts. So right now you can see I have the potentiometer set up such that I have about 800 millivolts, and I have about 5 volts being output. So I can then check this at various values. And in fact, what I probably want to do is take a few different measurements here. So we'll measure that right there. We'll say that's 500 millivolts and 0.243 on my output. We'll adjust that a little bit higher. So 606 millivolts and 1.902 output, 0.679, and 3.179. So to be clear here, I'm not trying to do a detailed analysis on this. I'm mainly just taking a few representative values to see if I have the gain set where I want it to, because I might need to make an adjustment. For one thing, the values we had in the equation assumed a 3-volt input at Vref, whereas in this case, we actually have a 3.3-volt value at Vref. And then let's just take this final value. So if I quickly plot these in Excel, I see that one, they're very linear, but I'm a little bit off from where I want to be. So remember, the values we were looking for is 16.2 and 6.4. Sorry, 14.2, 16.4. So I'm a little bit steeper, and the important part of this is I'm actually going to hit 0 before I get all the way down to my minimum value. But because I have used these potentiometers, I can now make the necessary adjustments to get this closer to what I'm looking for. So I can't really adjust Vref because I'm pulling that directly off of the 3.3, but I can adjust these two resistors until I get the necessary value. So that's sort of the strategy that you're going to want to use to obtain this relationship between your input and output voltage. The other thing I would just add to this is you don't need to exactly get this value, right? If I'm a little bit off, it doesn't matter. You'll still be linear. It's just you may not get the full range of temperatures. So that's something to keep in mind once I do the calibration. Also, this is not a calibration. This is just fixing the gain. What we want in our final calibration is a temperature that we read out with the something like with a thermometer, similar to what you did with the SkeeterSat, and have that go to an ADC value that will be read by the Arduino. So to make the actual temperature probe, you're going to duplicate the same process that you did with the thermistor, except you're going to have the diode in there instead of a thermistor. So we'll need to take our diode, we'll have to solder wires onto here, then heat shrink and liquid electrical tape that. So because of the cure time of that, you probably want to do that first. But if we use a setup like this potentiometer right here, that basically allows us to get the gain all set up, and then we just need to swap in our resistor. So that's how you want to set up your your temperature sensor. So then the second part is we need to set up the pressure sensor. So if you look at the data sheet, and this actually applies to several different models, but basically, one of the numbers here tells you, is it a 0 to 2 psi, 0 to 5? 0 to 15, 0 to 30, right? And the only difference is what is the full range. But the way this works is you supply current into pin 4, and pin 2 is your negative, and then you create this differential signal on pins 1 and 3. So what you'll actually see is basically at pins 1 and 3, you'll have a difference of about 100 millivolts. And the way you know that is if you go up to this full scale output span, it'll have a typical value and a min and a max value. So what we expect is about 100 millivolts. But we don't really, this could be 210 millivolts and this is 200. We just know the difference between the two of them is about 100 millivolts. So because of that, we need a different kind of amplifying circuit. In this case, we're going to use what's called a differential amplifier. So what it will actually amplify is the difference between the two signals. So in this case, our positive, slightly higher signal will be supplied here at A, and our slightly lower signal will be supplied here at B. So this would be like 2.1 volts, and this would be like 2 volts flat. The first part of the circuit that they go through is a simple, what's called a voltage follower. And that is just a non-inverting amplifier with a gain of 1. And you may be wondering, well, if I'm not increasing or decreasing the voltage, why would I run it through this amplifying circuit? So if you go back to the data sheet, you'll see that you have this setup of 4 resistors that is how it generates the output signal. And this is a circuit called a Wheatstone bridge, and it's very sensitive to slight changes in the current. So we don't want to be drawing any current out of pins 1 and pins 3 because that could also affect our signal rather than just changes in pressure. So the way that you accomplish that is you run it through something like this, because the output current will actually be coming from the voltage supply, not the input signal. You can see the input signal is not directly connected to anything downstream of the op amps. And then we have this second stage of amplification, which is actually what's going to take the difference of the voltage at pins 3 and 2, which is going to be the same as the voltages at A and B, and amplify it. So again, you can calculate what this equation will be for the output signal in terms of VA and VB and all of our resistances. But we can make one easy simplification is if we match R3 and R4. So we match R3 and R4, R3 and R4, and we match R1 and R2, R1 and R2. This equation simplifies greatly. It just simplifies into our output voltage is R2 over R4 times the difference between VA and VB. So if we remember back on our data sheet, we expect about 100 millivolts, and we want this to go from 0 to 5 volts. So that means we want R4 over R2 to be about 50. That'll take 0.1 volts and multiply it up to 5 volts. So if we set up the circuit and go back to the cameras, so here is my pressure circuit. I have the power just coming over from my second breadboard. You don't need 2 breadboards. You can fit this all on one, but it's a little bit easier for people to see if I spread it out. And I have my 2 first stage amplifiers with the second stage amplifier in the middle here. So my power comes in, it goes through this resistor right here, and it goes into my pressure sensor. I have a ground connection on pin 2. Pin 4 is where I supply my power, and then I have pins 1 and 3 going out. So if I was to look at the voltages, I could measure the voltages at pin 1 and 3, and right now, since I haven't decreased the pressure, this should be at its maximum value, so around 100 millivolts. And then if I look at my output value, if I've set everything up right, I should get 5 volts. So again, if I hook my circuit up to my multimeters, well, actually just the single multimeter, I switch the camera over so you guys can see it. You can see that I have about 5 volts set up here. Now, to calibrate it, you're going to need some sort of pressure device. So what we recommend you use, if you have access to it, so we have these little brake bleeder gauges. So what these are meant for is sucking the air out of a brake line, but you can see that we have tubing installed onto the end of it, and then this has a little bit of tubing and a little adapter that you can then put on the sensing port of the pressure sensor here. So if I install it on there, and then I pump the hand pump here, you'll see the pressure goes down. So this, let me get that so there's not glare on it. So this right here is a vacuum pressure gauge. So what it actually tells you is the pressure in whatever units below ambient pressure. So this outer scale is inches of mercury. So it goes from 0 all the way down to -30 at the lowest value. So for example, right now it's about 17 inches of mercury. So that means the pressure in this tubing and the pressure that the pressure sensor is sensing is 17 inches of mercury, or 400 millimeters of mercury, which are also called torr, if I remember right, below whatever the atmospheric pressure is. So in order to find out what the actual absolute pressure that my sensor is reading is, I would need to look up what the ambient pressure is based on like a weather report, and then subtract the appropriate value. So if we switch over to the multimeter camera, you can see that my voltage is lower because my pressure is lower. If I hit the release on this, I go all the way back to my maximum value. And you can see I can pump this down, you know, to get to a small value of about 1/2 volt. So at some point, basically, air is going to, this setup is going to start leaking Also, you want to be careful about making sure the pressure sensor doesn't get knocked off of the breadboard while you're trying to do this. But once you get your circuit working, you're going to want to then calibrate it using a pressure gauge, and then whatever, again, you will need to have the Arduino set up and reading out ADC values.